So I sent out an email late yesterday afternoon when I finally got this rep. This is lecture 3. We're moving on. So where we've been so far, the world of generalized linear models. The term "ized" means some kind of not normal outcome. So we have a link transform conditional mean that's being predicted by the model. Then we swap out whatever type of distribution we need to get the height, and that's how we find what the model parameters are. And I have a note, by the way, for those of you who've been in the multi-level stuff, the linear predictor includes the random effects. It's the level 1 conditional distribution that changes. Level 2 distributions always stay multivariate normal for the random effects. So in terms of a list here, purple versus blue, and I realize that may not render very well, but the purple part refers to the link function that we need, and the blue part refers to the distribution. In reading some of your formative assessment answers from Tuesday, I got the sense that maybe we weren't clear on like which is which based on the conversation. So these are two different things. The logit is how you transform what's being predicted into something that's continuous. So logits, probits, tobits, log-log, complementary log-log, those are link functions. That is required anytime that you're predicting an outcome that has a boundary. So zeros and ones is the example we have so far. Ordinal data, 1, 2, 3, 4, 5, for instance, nominal data, those need link functions to ensure that we don't predict, a 5.6 if the scale stops at 5, that kind of thing. In terms of the distribution, though, then it's a question of what are the possible values that an outcome can take. So if I have binary data, it's only zeros or ones. That goes with the Bernoulli distribution for 2 categories. If I have more than 2 categories, that goes with multinomial. So you can think of Bernoulli as a special case of multinomial with 2 categories only instead of 3 or more, or you can think of it as a special case of binomial for 1 trial. That's coming up later. So there is a phrase in Stata in particular, and I've seen it elsewhere, they call it multinomial regression. I don't like that phrase because that doesn't make any sense. Both ordinal and nominal outcomes use the multinomial distribution. That's just a distribution that has more than 2 categories. It's discrete. What separates what separates ordinal and nominal, though, help me out, what distinguishes these 2 things if it's not distribution? What's the purple part? How do I know if I have an ordinal model or a nominal model? If they both use the same distribution. You all nailed this on your quizzes. This part you got. Remember the submodels? How they divide up the categories differently? So the idea of the submodels being like 0 versus 1, 2, 3, 0, 1 versus 2, 3, or 0 versus 1, 0 versus 2, 0 versus 3, those are 2 different kinds of submodels, right? That's how. It's the link function. So ordinal goes with link functions that are cumulative. They create binary submodels that use all the categories and they enforce order. So the model guarantees that the probability of high belonging, for instance, is going to be higher than the probability of medium belonging, which is going to be higher than low. The model enforces that ordering through the cumulative logit or probit link. Nominal is the version that is like dummy coding. You pick a reference outcome, and then the submodels tell you the probability of each other outcome relative to that reference. So it's different link functions that lend themselves into different kinds of models that distinguish ordinal from nominal. They both use the same kind of distribution. And what's nice about these, by the way, Bernoulli and multinomial, these are the only choices. You cannot be wrong. From this point forward, you can be wrong. Which distribution to pick is an empirical question where we will look at different alternatives and see what the data like best. So we're changing gears in the sense that the hard part about categorical data, to me, is managing the link functions. Like, okay, I'm in logits, but what is it the logit of? Is it a 1? Is it a 0? Is it the higher? Is it the lower? Is it this one versus that one? Like figuring out what the model is predicting is the hard part. The links for categorical are the difficulty. The distributions are, this is what you're stuck with. The next unit that we're in here, counts, the link is the easy part. It's going to be log, the end, the natural log in particular. But then I have in here for blue, for distributions, some kind of Poisson or negative binomial. We're going to talk about 6 different alternatives that they could be. And 4 of the alternatives come into play if you have what's known as a zero inflated count, meaning you have a giant pile of zeros in your count followed by some kind of distribution of counts after that. So that's the unit we're in right now. And coming up later after spring break, we talk about proportions. I don't have time for an example of censored data, but I have this included in the list as part of that, and then skewed continuous as well. So the taxonomy. Yeah,
sorry
please.
to bother you, but can I go back to that slide? I mean,
This one.
so
Yeah.
what I remember from counts is that is continuous variable.
It's treated as, yeah, so continue-ish is a word that I make up.
Yeah, it's your word? Yeah.
It's my word, yeah.
Okay,
Because oftentimes when people have count data, they pretend that it is continue-ish, like us. I can't say it right. Continuous. There we go. O-U-S, that one. This is how I know I need a break. I can't, my English is gone, right? The long language I should have is gone. That's not a good sign. But in practice, right, people will be like, oh, it's a count, but it's a number, so it's fine. But in terms of distributions, though, counts don't have intermediate values. Like, counts are discrete. You have 1 thing or 2 things or 3 things or 4 things. You can't have 3.5 things. So from that perspective, it falls under the heading of what is known as a discrete outcome, even though it is a number, and it acts like a number.
So actually what I was gonna ask is that count variable has the one with 1 boundary, if I understand correctly.
That's correct.
And I saw some zero inflated something there, so can you please explain what that means?
Yes. Let me foreshadow with a picture. This is slide 17. I'll just do this slide right now. This is a good example. This is an example that I stole from this publication. So it was a tutorial on count regression models, which I liked. And this x-axis is the variable that they were analyzing, which is the number of steps taken towards divorce in married couples. A nice cheery outcome for our pre-spring break lecture. And this pile of zeros right here has potentially 2 different kinds of people contributing to it. So this is what's known as a zero inflated distribution, because it looks like there's a whole bunch of people who said, I've taken no steps, and then there's people who admitted to taking some steps after that. So like if this followed a normal count distribution, you would not have this many zeros. And they overlaid the prediction from count distributions. So Poisson is the one we're going to start with. That's the solid gray line. That's this right here. This one. If this were a regular count distribution, this is how many zeros you would expect, this dot right here. But there's way more than that. So that additional number of zero values beyond what the distribution expects is referred to as zero inflation as a term. And this pile of zeros right here, this is my language here, there's 2 different kinds of people. Like there's me as part of one of them, hi honey, steps towards divorce, I would never. Don't even ask me that question, 0. Versus someone else that's like, yeah, 0 because I haven't gotten around to calling a lawyer yet, but I'm gonna. Right, there's, like the steps towards divorce is inferring a population that's heading in that direction, and the question is, how far on that road are you? Whereas some of the people saying 0, like you could ask them every single day of their entire life and their answer would still be 0. Hi, honey. So then the question is, how do you want to model that? And there's different choices for what you do with the zeros for zero inflation. But this is the kind of picture that would lend itself to it. Also, another classic example, number of cigarettes you smoked this week. Right, I'm a non-smoker. I've actually never smoked a cigarette in my life because I hate smoke. So no matter which week you ask me, the answer is going to be 0. I'm a non-smoker. And then it may be that there's some people who just, they ran out of money and they haven't bought their cigarettes for the week yet, and so it's 0 right now. But they're part of the smoking distribution. The same thing might happen for something like other kinds of drug use, alcohol. Some people drink, some people don't, that kind of thing. So anytime you're mixing together like qualitatively different kinds of people and asking them how often they do something, the people who would never do it are like what people call structural zeros, that's a term, and then the rest are expected zeros based on account distribution. So the question is, what do you do with all the extra zeros? That's one of the distribution choices. Okay, does that help?
Clear, thank you.
Okay, so slide 17, we're not there yet though, but there's a picture. All right. So then the things that we need to worry about in terms of predicting different kinds of outcomes. So the distributions that we would draw from, that are our choices, a menu of options, so to speak, discrete kinds are appropriate when the responses are whole numbers. So categorical is the example we looked at first, in which these aren't really numbers, right? Like I could say some belonging is 1 and medium belonging is 2, or I could say some belonging is -6 and medium is 12, right? They're not numbers, they're just labels. So there's a sense in which the numbers are arbitrary. We're not treating them as numbers, we're treating them as discrete categories. And in this context, the easy part is what distribution they go with. It's literally just the number of choices. It's multinomial if you have 3 or more, and it's Bernoulli if you have 2. That's it. The question then is, what link function do you want? And that's which kind of order, and then do you want your slips to be different across the submodels or not? Like those are the things that we worry about with categorical. Counts then are bounded at 0. I can't drink -1 drinks, right? That doesn't work. I can't smoke -1 cigarettes. The lowest I can do on a scale like this is 0. So the outcome is bounded at 0, and it's limited to whole numbers. I can't report that I had a drink and a half. That doesn't work. Or I spent, I don't know, you get the point. And in this case, it's the log link. That way we keep everything above 0. The tricky part is what kind of distribution we want. So there are sort of 2 families, Poisson and negative binomial. You'll see those in just a minute. And then the question is, what are we going to do about these extra zeros if we have those? Continuous outcomes then are responses in which the numbers are numbers and you can have non-integer values. So things like response time in milliseconds, blood pressure, like you can have fractions of things. They're truly continuous. And for outcomes like this is the unit after the current one, the question is, are they skewed and is there a boundary? So for instance, like home prices is one of the examples I'm going to have. What's the cheapest a home can be? I don't know, like free, I guess, maybe if you inherit it from your family or something like that. What's the most expensive that a home can be? I remember that when I gave this example like 2 years ago, there was a story in the newspaper about the most expensive house that had ever been sold, and it was like hundreds of millions of dollars somewhere in California, right? It can go up to forever. So home prices is an example of where you could have a home that cost, $116,374.52. Like you can have that. That's a possibility. But homes don't go below 0. Blood pressure does not go below 0. I'm pretty sure that's bad. I haven't gotten to that season of Grey's Anatomy yet, but I'm pretty sure that negative blood pressure would be a bad sign. I'm rewatching Grey's Anatomy right now. So I'm in season 9. Maybe by the time it comes back, I'll be ready for season 20 or wherever we're at there. But I gotta tell you, when I first started watching Grey's Anatomy, I was a postdoc. And now that I'm a grown-up, it hits completely differently. I loved Christina back then. Now I'm all about Bailey. Like Miranda Bailey is my hero, like throughout that entire series. So I just watched her get married last night. It was beautiful. Anyway, I'm off on a tangent. Grey's Anatomy, blood pressure cannot go negative. So even if it's continuous, it could still have boundaries. That's where we're going. So then the question is, how do we deal with that and those types of outcomes? The counts, the link part is super easy. It's logs. So we are going to predict the log of the expected count. And this is where the notation gets a little bit ugly, so please bear with me. If you can hang on to that idea, what the model is predicting directly is in the log scale. To unlog it, we're going to do the same thing we did before, exponentiate, e to that. So the same type of transformation that you're used to going from logits down to odds down to probability. It's the same idea, just with one step removed. So we are predicting the log of the expected count. That's the conditional mean. So for instance, if I have a model that looks like this, if the y-axis is the log of the expected count, then the slopes are going to be linear. So beta 1, if it's positive, will be the blue line. If beta 1 is negative, it's the red line. But when we back translate these predicted outcomes onto the original scale of expected count, so e to the prediction, exponentiate each of these predictions, then we get these bendy lines that look like this. So in particular, the positive slope, it shuts off as you approach an expected count of 0, and it goes like this. So we have this sort of bendy line heading up towards infinity that is predicted by the model. So nonlinear slopes when you translate into expected counts. So in terms of notation, the link function, so the dot in the middle, we would replace with the expected value of y. What the model is predicting is the log of that. And so instead of saying expected value of y, the notation that's used in the textbook I'm using, the Stata book, is mu. So mu is in the data scale. The log of that then is being predicted by the slopes and the predictors. Inverse lengthening is written like this, where the e part is that. So the expected value, if we want to get that back out of our model prediction, it's e to the prediction. So the model predicts logs. To unlog it, we exponentiate. That's the big picture. And this e to the y thing is important because the expected value is not just discrete. It can be continuous. So in the same way that we had binary data we start with, we had zeros and ones, right? That's the column of y that goes into the analysis, and we don't touch it. We don't transform it. We don't try to logit it. We don't do any of that. We got my zeros and ones. What the model is predicting is the probability of a 1. That's the expected value. So in this case, we're predicting the expected count. So let's say that I get an intercept back from my expected count of -1 in logs. If I exponentiate that, so e to the power of -1, that creates an expected count of 0.368. So this is the mean of the count variable. The mean is not discrete. You can have an expected count of 0.3, of 6.12, of, a million point whatever. Expected counts have a full continuous range to them. You can control for differences in the amount of time measured with something called an offset or an exposure. I don't have that built into my example, but that would be useful anytime you have differences in expected counts. So as an example of that, let's go with something like crime rate, or number of murders that have been committed in a given county. Do you know where there's going to be more murders? Places where more people live. So if you just were to predict the count of fatalities, that's going to be misleading because the count's going to be higher where there's more people. So that's why people talk about crime rate as opposed to just crime amount. And if you have different amounts that are possible, you include that in the model as what's known as an offset, which is essentially a predictor whose slope is fixed to 1, and that turns it into a rate. So then you're talking about more crimes than would be expected based on your population size. So in the context of child development, you might have an observational study that goes into a classroom and counts the number of times a child interrupted their teacher or something like that. If you watched one kid for an hour and you watched another kid for only a half hour because then they got kicked out of class or something, right? The kid who was only watched for a half hour doesn't have as much of a chance to show misbehavior. So an offset would correct for the differences in base rate, essentially. Guess what effect size is in these models? New word, same idea. Odds ratios, still. But now they get yet another word. So it was called an odds ratio in predicting binary outcomes, e to the slope. It was called a relative risk ratio in a nominal model, e to the slope. Now it is called an incident rate ratio, e to the slope. Same operation, different words. So the same scale is in effect. If I have a slope that is negative, what is the possible range of my IRR then? What range would negative slopes go with? 0 to 1. If I have a slope of 0, what does that translate into in an IRR? 1. What if I have a positive slope? What does that translate into? 1 to infinity. Yes, same thing. So we're still using e to the slope as an index of effect size in these. So a couple examples. If I have a slope for a variable that is binary, so a binary predictor x, and my effect size for that slope is 1.25, I would say the counts are 25% higher for someone who has a 1 for x instead of someone who has a 0. If it were a negative slope, so then the effect size is 0.75, then I would say the counts are 25% lower for someone who has a 1 on x instead of 0. Same thing. So this is the easy part. The link is log, the end. Effect sizes, e to the end. Distribution is the hard part. Questions?
Yeah, so I have two questions. One of them is the percentage of talking. Okay, first, let me back up.
Okay.
X is a predictor.
X
right?
is predictor, yeah.
And in this case, it's a binary predictor.
Yes.
Is the fact that we can talk about like 25% higher or 25% lower, the fact that we're dealing with counts?
I would say that it's more general than that because it's like the odds is what gets higher or lower in binary, but we don't have that middle layer of odds for this. So it's just the counts are this much higher.
Okay. Cool.
Because once you exponentiate, you go from log scale back down to data scale
Yep.
of expected count.
Yep.
So then it's like the counts are what's higher or lower, not the odds.
So odds are still stupid.
Odds are still stupid, yes, we have
but
not.
This
Mhm.
makes a little bit more sense.
Yeah, this is easier because it's a 2-layer cake instead of a 3-layer cake. We don't have logits to odds to probability. We're missing the bottom layer technically, but I don't know. Anyway, logs or counts, that's it. Okay, now the distribution part is the tricky part. So here's some choices. I stole this from Wikipedia, as I tend to do. Wikipedia decided that lambda would be the parameter of this distribution, and I was like, I can't have lambda, that's a factor loading, damn it. I'm not going to confuse these people any more than I already have. So mu is lambda in our notation. But here's the Poisson distribution. And this picture has dots for each point on the distribution to emphasize the fact that this is discrete. So this distribution has whole numbers to it only for counts. And if the mean of the distribution were 1, that would follow the orange line here. If the mean of the distribution were 4, that would be purple. And if the mean were 10, that would be, I'm not going to call this cyan, maybe periwinkle, something like that. Can we go with periwinkle? Judge's ruling on the blue here. Now, if you just look at the blue line, does that shape look familiar? Yeah, it looks normal, doesn't it? Or Gaussian, if you want to sound fancy. It is. The Gaussian distribution is the normal distribution. So back to the 1600s or whatever. So to your point, Sora, continue-ish. Yeah, once your expected counts get above about 6 or so, a normal distribution is not unreasonable. So like counts that are really high, you can probably ignore the fact that they're bounded because your predictions are not going to go anywhere near 0. If you have, a lot of zeros in your sample, though, you want to make sure that your predictions stay off of 0 like they're supposed to. So this distribution is special. I have lost my power of speech. I hope to get it back after break. It's special because this one doesn't have a variance to it either. So in binary distributions, Bernoulli, the mean is the proportion of 1s, and the variance is the proportion of ones times the proportion of zeros. Same principle operates in multinomial. Here, the mean is the variance. According to this distribution, it's one number. So that means as the mean increases, like if I have a predicted count of 12, the variance around that prediction is 12. If I have a predicted count of 5, the variance around that is 5, it shrinks. If I have a predicted count of 1, the variance around it is 1, and it shrinks further. So variance is non-constant. It increases directly with the predicted mean of the distribution. And that makes sense if you think about predictions being wrong. Like, if I predict your count is 50, there's a lot of room for me to be wrong on that. If I predict your count is 1, I can't be that wrong because I have to be above 0. So if you picture like error bars around a line, like you should see them shrink as a function as you get closer and closer to 0, because this distribution says the mean and the variance are one number. And here's how we're going to estimate it. Yes? Yeah, in this, they use the lambda as the parameter, the one parameter of this distribution that's estimated, and it is both its mean and its variance. And because this is a factor loading in my other class, I'm using mu, which is the notation that's consistent with the idea of the interior on the data scale that's being predicted. The expected value of y is the mean of y, and that's mu in our notation. And it stays mu throughout the book, the state textbook, and all of their explanations of things. So yeah, this is not a factor loading. And also, this is not an exclamation point. It's not like, why? It's the factorial of y. All right, so this is nice, but it never works. I've never seen this hold in data, ever. But it's the jumping off point for things that will work. So we're going to take this and we're going to add stuff to it to make it work. So there's 3 reasons why this might not work. Number 1 is that usually the mean and the variance aren't the same. The variance increases more than the mean. There's extra variance relative to what Poisson expects. So if you have too little variance relative to what the model expects, that's called under dispersion. So dispersion is like this idea of how spread out things are, how dispersed. Under dispersed means less variable than is predicted by the model. If you have more variance in the mean, that's over dispersion. So this is a new vocabulary word, over dispersion. Extra variance relative to what is expected from that distribution. That's what over dispersion means. This is the one that I see most of the time. So there's one solution for that we're going to use, which is going to be the negative binomial model, or distribution, excuse me. Another one is if there's no 0 values. So you can have counts that start at 1. Can you think of any examples of a count outcome that would start at 1 instead of 0? Vladimir, what do you think?
Ounces of water, maybe?
Ounces of water?
Glasses of water?
Glasses of water? Like
I
how?
don't drink water.
Yeah, so everybody has to drink at least some water?
Yeah.
Yeah, I hope you're right, but I know people that would have a 0 in that distribution, right? Like, I bring a full thing of water every time. I never freaking touch it. I'm always, like, sucking on my soda can here. With the little straw, because this I developed when I was teaching in a mask, and I'd shove the straw under my mask, and so I just kind of kept with the straw. But yeah, theoretically, yeah, Sora's like, I'm going to drink my water. Here, let's all just chug our water for the sake of health for a moment right here. Yes. What if you're dealing with secondary data? Let's say that you get data from a prison, and you're looking at how things related to maybe disruptive behavior in the prison and prison sentences and demographic variables all relate to each other, like who's more likely to be in prison, that kind of thing. So if you have a variable like how many times have you been arrested, and you're using a prison data set, everybody got arrested or they're not in prison. At least one, right? Or they don't qualify. Same thing if you get data from secondary education. How many colleges have you attended? Well, if you're in my data set, you're at the University of Iowa. You've attended at least one college. Hospitals. How long have you been staying in the hospital? If you're in the hospital data set, you have stayed in the hospital. So there are contexts in which the counts start at 1 or start at some other model. And when I first learned about this, I was like, well, I can fix that. Let's just subtract 1. Problem solved. It doesn't work that way. It didn't work. You don't get the right answer. The answer is that you need a different distribution that bounds at 1 instead of 0. That's the answer. And then problem number 3 is when you have too many 0 values or 0 inflation, the picture that I showed at the beginning of class. So these are 3 different issues that can come up, and they each require a different adjustment to make it work in terms of distribution. Okay, how are we doing? Now, why do I give a shit about distributions? You might be asking yourself that, because I know you don't, right? Like, no one woke up in the morning and was like, research question 1 is, does my outcome follow a Poisson distribution or a negative binomial? Like, no one ever wrote that in your thesis. And if you did, your advisor's like, that's not your research question. So why do I care? If I get my distribution wrong, what are some downstream consequences of that? My analysis is wrong? Maybe. Parts of it are going to be wrong. Will my slopes be wrong? Intercept is going to be my expected outcome. So if I throw a log link on that, right, then I'll have the right predictions that stay within the boundaries they need to. But what about my conclusions? How do I know if a slope matters? How do I know if a slope should be part of my discussion section? I can think of 2 things, effect size and significance testing, right? That's usually what we would refer to. Well, how do I get a p-value out of my slope? Well, the test statistic next to it is significant, right? So how do I get my z or my t? Where does that come from? Let's back over the columns. Actually, this way for y'all. Columns to the left. What's the next column over?
Standard error.
Standard error, yeah. So estimate divided by standard error is my test statistic, which gives me my p-value. So standard errors are based on our model for distributions. If I have a normal distribution, then my standard error is a function of 1 number for the variance, plus some additional stuff related to values of x that I'm generating my prediction for. But 1 number for the variance is predicated on the idea of the normal distribution. It has a variance in it as an estimated parameter. So that means that all else being likely, the same window around my prediction would be for every case, because variance is supposed to be constant. This is not saying that. This is saying, no, variance is going to shrink as you get closer and closer to 0. Variance grows with the mean. So that implies standard errors that are dynamic, if you will. They change as a function of where you are. And so your inferences about them would change as a function of where you are. So link functions, putting it together, link functions are designed to make sure that your predictions behave. They stay within the boundaries that you have. Distributions are designed to give you the most correct version of your standard errors and the most believable version of your hypothesis tests. That's why we care. So we might come to the wrong conclusion with the wrong distribution. And in fact, can I tell you the story that motivated example 3? Why not? We like stories, right? It's a true story. Okay? So this is a true story from my days at Nebraska. And I had a student come to me. I was our department consultant in the Department of Psychology. And she had a question about what kind of transformation she should do for her data to make it normal. Okay, so you're taught to check assumptions, right, when you look at regression models and things. And if your residuals aren't normal, then you should transform your outcomes so the residuals look normal, right? Okay. All right, I'm like, okay, well, what do you mean? What kind of distribution, like what kind of transformation, what type of outcome do you have? So I'm opening up what is going to be example 3, this so that I can show you the picture. This is from the last time I taught the class. I haven't updated it just yet, but it's starting. It's thinking about it. It's thinking about it. The story behind her outcome was that she was doing an experiment and she was deliberately pissing people off as part of this experiment. That happens. It got IRB approval. And so,
LOL, but I can't email people more than 3 times.
yeah, no, it's totes fine. And actually, this same lab got permission to get people drunk and then piss them off in a different study. So yeah, I did not want to be part of that analysis, but so this is the picture for her distribution. This right here. Okay. This outcome is number of mean things people said to their partner while they were pissed off at them, okay? Excuse me, number of aggressive verbalizations. So she showed me this picture, and she's like, what kind of transformation do I need? I'm like, I'm not a math person. I think we've established that, but I don't know of anything that I can do to a column of zeros that is 45% of the data to take this constant and turn it into something other than a constant. Right? These are zeros. Like that is what it is. These are people who said no mean things. So I'm like, there is no transformation. This is a count outcome. And it turned out that I'm pretty sure the reason she came to see me is because the test of the interaction, that was the whole point of her master's thesis, had a p-value of 0.06. So they're like, how can we make this work? And I was like, okay, no, but I can still help you. And can I have your data to make a class example out of it? I'll help you if I can have your data. And she's like, cool. So then, yeah, I know, it's true story. So yeah, here's a plot of the interaction. It looked like there's 3 different conditions, and there was an interaction with a background variable as to whether they had a history of intimate partner violence, and it turned out that telling people to stuff their feelings down and don't do anything is bad for you. Okay, don't do that. That's this condition. So it looks like people's reactions to these manipulations turned out differently based on their background status. That was what she wanted to know. And yeah, sure enough, the interaction term for a normal model, we get to that. Show you, this is the example that's coming. Where is it? Where is it? Where is it? I can't find it. Here. Right here. Here it is. Here's her p-value for her interaction. 0.0579. Heartbreaking, right? But it turns out if you fit the right model, then her interaction is wildly significant. So this is the story I'm going to tell you. This is why we care. Get the distribution right, then you come to more accurate conclusions. That's the idea. What's the model? She fit an ANOVA. It was a 2x3 factorial ANOVA because that's what she knew how to do. So I was like, you're going to fit a 2x3 factorial ANOVA, but you're going to add a log link, and you're going to switch it into a count distribution. And not only did it work, it got published. So, and she graduated. Now she's off in the world doing her business. So congratulations to her. There, how's that for a story? This is why we care. Because the inferences that we're making depend on getting the distributions as right as we can. And there's absolutely nothing wrong with ANOVA if you have a continuous outcome. But she had this outcome of number of mean things that people said, where half the sample said no mean things. And there's no way to transform that into something that's continuous. It's not going to work. Okay, so fix the first problem. Well, if the mean is not going to be the same as the variance, if the variance doesn't grow directly with the mean, then let's tweak it. All right. So we get into a different distribution called negative binomial. It's ugly. Here's the formula for it. Here's an easier version. This little piece right here. The negative binomial distribution adds an additional parameter. It's known as a scale parameter or a dispersion parameter. I've notated it with K. And I call it the stretchy factor. Like in a rubber band, elastic, stretchy. Same principle. It's a multiplier. So what it does is say, okay, so the variance needs to grow with the mean. So the expected variance is going to be whatever the mean is, mu, plus this stretchy factor times the mean squared. So what that does is add extra variance in a quadratic pattern with the mean. Here's a picture. I didn't steal this one from Wikipedia. I made this one all by my own self. Aren't you proud of me? Like, no. This is why I steal, because it's a lot faster to do a Google image search and borrow stuff from someone else. But I remember making this one in part so that I could make sure that I knew what the hell I was doing. So this one contrasts two different versions of a curve with the same mean. So the blue line and the red line, these two, these are both count distributions that have a mean of 5. The blue one is straight Poisson, in which the stretchy factor is set to 0. So this is what Poisson looks like. The red one is called negative binomial, and it has a stretchy factor of 0.25, which when you throw it into the formula here, it means the expected variance is 11.25, not 5. So that creates this red line here that has a little bit more skewness. Same thing with green versus purple. Green is straight Poisson with a mean of 10, no stretchy. Purple is negative binomial with a mean of 10 and a little bit of stretchy, and it makes it skewed like that. So this purple line, this is very common for count data. You see that it's bounded at 0, but there's a chance that you can have some people with super high counts as part of that. So whenever that happens, you throw in a stretchy. And the way that this is worded is if k is 0, the second part of this falls out, and you're left with just straight Poisson. So we can do a test whether we need k or whether it's okay to set k to equal to 0. And here's the good news, folks. You already know how to do this. Can you think of a way to see whether you like one model that adds some stuff better than a model that doesn't have the stuff yet? Looking for a 3-word phrase. First word starts with an L. Second word starts with an R. Third word starts with a T. Likelihood ratio test. Yeah, difference in -2 log likelihood. We're going to do that again. So because you can think of Poisson as nested and negative binomial, the difference is whether or not you need k to be something other than 0. That's a likelihood ratio test. However, statisticians will tell you, actually, not quite that simple. Because k can't go negative. It's bounded at 0 in the way this model is being estimated. So instead of using a cutoff of 3.84 for the one extra parameter between the two, we should actually use what's known as a mixture chi-square for the situations in which k would want to go negative, but it's not allowed. And that essentially cuts the p-value in half. So the critical value for saying that k is needed and that negative binomial is a better choice than Poisson is 2.7 instead of 3.84. And if you're like, who the hell cares, Lisa? Those are like the same. Yeah, you're not wrong. Only if your difference is between 2.7 and 3.8 do you need to worry about this. If it's greater than 3.8, you're good to go. So it's a fairly low standard. All right. So big picture, predicting counts. What link are we going to use? Log. Why aren't we using logits? What are logits for? What kind of outcomes? Categorical, that's right. And more generally, in categorical data, are we worried about predicting too high? Like a probability of 1.2? We're worried about that, right? Are we worried about predicting too low? Like, can't have negative probabilities? So we have two boundaries. Logits are designed to reel things into two sides. Log is lower bound only. So we don't want to stop the positive counts. We can let the positive counts go to infinity, right? I can take 8 million steps towards divorce or smoke 7 million cigarettes. Like Like, that could be my reality. We want to let that happen, but we don't want to have a predicted number of cigarettes smoked of -5. We don't want that. So that's why we do logs. So then the question is, what distribution do the counts follow? And here are 2 choices. Poisson is the base. Negative binomial is adding an extra stretchy factor, and we can test whether that's needed. Okay. 310. How are we doing? So foreshadowing, one extra thing to be talked about after break. If my likelihood ratio test is significant, that means negative binomial is better than Poisson. We need the k to be something other than 0. Or we could say it the other way, Poisson is worse than negative binomial. But how do I know if either of them is any good? Like, if you ask me, would you prefer to have a hamburger from McDonald's or Burger King? I would say no. I would not. But if pressed, I would have to say, I think McDonald's is shittier than Burger King. That's my preference. But you didn't ask me the question, like, do you want to have a hamburger from them at all? Because the answer is no. Only if I'm stuck in O'Hare, Terminal F, in between flights, and that's the only choice I have against starvation, will I buy a McDonald's hamburger. So that's the idea of absolute fit, right? Is this model any good in an absolute sense? Because all we know is that something is better than something else doesn't tell if it's any good. So we have yet another thing we have to consider to find out if it's good enough in an absolute sense, not just relatively better or worse than some alternative. Okay. That's after break, though. And tonight we're having Steak and Shake. So, whose hamburgers I have gotten used to because it's my son's favorite thing on earth. So, yeah, it's his birthday. So we're having Steak and Shake for dinner tonight. Yeah, and tomorrow I probably won't need food because I will be eating 7,000 calories for my dinner tonight. Because it's not just the hamburgers, it's the French fries and the onion rings and the milkshake, and it's like a whole thing. So that's what we're doing. All right, 3:12. Any questions as we wrap up for the week? All right, thanks for being here and hanging in there. So next week, no class, no office hours. I will have intermittent email. Otherwise, I will leave you alone. Good deal? All right, excellent. See you on the other side. Enjoy your break. Bye, Zoomers.
I'll keep you updated.
Okay.
On the things I mentioned.
1 second.
Yeah.